When I was in +2, I used to be very fascinated about multiple integrals, these double integrals and triple integrals. So in one of the previous videos when we were solving Gaussian integral, and that was this integral from minus infinite to plus infinite, e to the power minus x squared dx, we have used double integral to prove that the value of this integral is equal to under root pi. Now when we were discussing that video, there we have changed this double integral from x and y in terms of polar coordinates. That is, we have replaced x with r cos theta and y with r sin theta. Now in this video, we look at something called as Jacobian or Jacobian determinant. Now the first question is, why are we studying Jacobian or Jacobian determinant? Now we know that substitution is a very powerful tool in integrations. So at times it is easy for us to evaluate integral by making change of variables. So if we have this double integral, which is capital F xy into dA, and dA in this case will be dx into dy over this region R on xy, we can change this x with substitution. Let x equals fuv and y equals guv. Then we can change this integral as r over uv, then f, we'll replace x with fuv and we'll replace y with guv, and then there is this factor j. So we call this factor j as Jacobian or Jacobian determinant into dA, and dA in this case will be simply du into dv. So when we are applying substitution in double or triple integral, so when we need to change this area dA, then we change it in terms of this Jacobian and we write it as j into dA. And same is the case with triple integral also. So when we have this volume dv, then we change this volume into j dv. So j, Jacobian or Jacobian determinant, is the factor with which we are going to change this area or volume. Now the second question is, why do we need this factor j? So when we are changing the variables from xy to u and v, so this small area dA, so which is product of dx and dy, which in this case is a small square, it gets transformed into a distorted parallelogram. Jacobian determinant j, it gives the ratio of the area of approximating parallelogram to that of the original square. So this j, it actually gives the factor with which this dA gets converted into this new area, which is j into dA. And in the same way, this volume dv, it gets changed into j into dv. And there's this one more thing. So when we are taking this j, we are actually taking the modulus value of j or absolute value of j. How do we calculate this j? Now for double integrals, this Jacobian j uv, it is calculated as, so we have these variables x and y. Now we know that x is fuv and y is guv. So this Jacobian is expressed as del x upon del u, del x upon del v, del y upon del u, del y upon del v. So here we are taking partial derivatives. So we'll solve this determinant and we'll take its absolute value, and then we can change this dA or this dx into dy as j into du into dv. Say for example, suppose we have this double integral, which is fxy into dx into dy over this area R. Now we want to change this integral in terms of polar coordinates, and we know that for polar coordinates, x is r cos theta and y is r sin theta. So the first thing that we'll do is we'll find Jacobian for this determinant. So we know that j is del x upon del r, del x upon del theta, and this is del y upon del r and del y upon del theta. Now what is del x upon del r? So simply it will be cos theta. Now del x upon del theta, derivative of cos theta is minus sin theta, so it will be minus r sin theta. Now del y upon del r, it is simply sin theta, and del y upon del theta is r cos theta. Now we'll solve this determinant, so we'll get r cos square theta plus r sin square theta. Now cos square theta plus sin square theta is 1. So Jacobian for this transformation is simply r. Now if I have to change this integral in terms of polar coordinates, then I can change this integral as integral over this area r and then f. So I'll replace x with r cos theta, y with r sin theta, and then I'll change this dA, dx into dy with j into dA. So j in this case is r and dA is du into dv, which is dr into d theta. So this is how we can change a double integral from rectangular system xy to polar system of r and theta. So in that video of Gaussian integral, we have changed this dx into dy with r into dr into d theta. So at that point of time, we have not studied Jacobian. So I have skipped the portion like why we are changing dx into dy with r dr into d theta. Now we know why we change dx into dy as r dr d theta. So this is due to this Jacobian factor.